Now here's a little mix of examples and theory coming. Section 3.5. Some more examples of projection methods. And we start with the so-called collocation method. And this is particularly for function spaces. So let x and y be spaces of functions on an interval AB. For simplicity, let's assume the values are real. And then for every natural number n, you take a linearly independent family of functions in X. And the family has size n, so let's call them B1 up to Bn. Here's a simple example that is, however, often used. You're introducing some grid Gn on your interval AB, possibly equispace, but not necessarily. And usually you put the first and the last grid point equal to the endpoints of your interval. And then the first function B1 will have the following graph. It's starting at value 1 up here. And then it goes down linearly and it arrives at the axis when you reach the next grid point. And from there on, it's constantly equal to 0. Okay, that's your function B1. Now function B2 reaches the value 1 at the second grid point, and from there it decays linearly in both directions, reaching the axis at the previous and the next grid point, and then for the rest it's equal to 0. Similarly, B3 has its top at value 1 here in the third grid point, decays linearly and reaches the axis at the previous and the next grid point, and otherwise is equal to 0. Okay, and so on. And the last function Bn will reach value 1 at the last grid point, which is the right endpoint of our interval. And it will decay linearly to the left, reaching the axis at the previous grid point, and it will be 0 otherwise. You often call them hat functions. Well, the first and the last one is only 1/2 of a hat. And if your grid is nice and equispaced, then your hats will look nice and even. Mine do not, because my grid was not equispaced. Is it clear that this family is linearly independent? Well, probably kind of clear. You cannot write one of them, let's say B3, as a linear combination of the others, because B3 is the only one that is non-zero at the third grid point. All the others are 0 there. So how could you write the action of B3 as a linear combination of all the others, right? So this seems impossible. But of course we can attempt a proper proof of linear independence. And if you recall from your first year linear algebra course, you start by a linear combination of your functions. That is the 0 element of your space. Okay, but of course we know what the graph of the 0 element looks like. I hope you can still see that. Well, it's the 0 element is the function that is 0 always, so its graph is on the horizontal axis. So this function here is 0 for all values t between a and b. So in particular for the grid points, let's label our grid points T1, T2, and so on. So this equality here holds at every point T between A and B, in particular at the grid points. Now this right-hand side here is obviously always 0. And now remember that each one of our head functions is 1 at the corresponding grid point. So the third head function B3 is 1 at the third grid point T3. And if you check it at any other grid point, the value is 0. So in particular, B1 at Tk will give you a 1 if k is 1 and a 0 otherwise. Okay, and the same for all the others here. So maybe it's easier to write this as a summation. And then recall what we know about this function value here. So here you only get a 1 if the number of the head function and the number of the grid point agree. In all other cases you get a 0. So out of this sum here, only one of these terms is 1, which is the kth term. So only when j is k, you get something, otherwise you get nothing. And what do you get if j is k? Well, you get alpha j, which is then alpha k. Multiplied by 1, but I don't think we have to write that down. Okay, let's highlight what we just proved. For every k from 1 to n, we showed that alpha k equals 0. So in other words, the only choice of alpha 1 to alpha n that makes your linear combination equal to the 0 function is the trivial combination, where you put all your coefficients equal to 0. But that's of course how you prove linear independence. Okay, so that's where this example, this EG, ends. Now we come back to the general construction of the collocation method. Next thing you do is you introduce your subspace Xn, because in the end you want a projection method. And you define Xn to be the span of these n functions b1 to bn. And because b1 to bn are linearly independent, they now form a basis of the space that they span, which is Xn. And therefore this has dimension n because its basis has n elements. And okay, just because we have a concrete example here, let's try and see what elements of our space Xn look like in this particular example. So let me try to draw graphs again, and let's try to keep the original graphs visible. Okay, so the elements of our space Xn are now linear combinations, just like you can see them here. And now let's try to draw the graph of such a linear combination, which will obviously depend on the coefficients alpha 1 up to alpha n. Okay, now we're not looking at combinations that give you the 0 function, but at general linear combinations, okay? Okay, and the simplest point of this graph are the grid points, because at the first grid point, T1, we know that only B1 is giving us a contribution, all the others are 0 there, so we can ignore the rest of this term here. So at point T1 we should get alpha 1 times B1 at that point, but that is 1, remember here. So the value of f at point T1 is just equal to alpha 1. The value of f at the second grid point T2, well, it's just coming from this term because all the other basis functions are 0 there. And by the same argument you get alpha 2 times a 1, which is coming from here, so you get alpha 2. And then this goes on like that until the last grid point. Of course your alphas could also be negative, but that would totally destroy my artistic drawing here. Okay, but now what is happening? What's my function doing between these points? Well, I know it's a linear combination of my basis functions b1 to bn, and I know that my basis functions are piecewise linear functions, right? So b1 is linear here, and then constant, so also linear here. And the same for all the others, right? So they are linear, 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 and so on. And if you take a sum of multiples of piecewise linear functions, then what you get is a piecewise linear function. Okay, and you know that between the grid points nothing exciting is going on, because all the basis elements are having their kinks at the grid points, so there are no kinks or edges happening between them. So the answer must be that the graph is just this. So you just connect the points that you know by line segments, and that's the graph of your function f. And of course, every piecewise linear function on the interval AB, where the pieces are separated by our grid points, can be written in that form here. How do you have to choose the alphas? Well, you just have to choose the alphas equal to the function values at the grid points, and that's how you get your function f. Okay, so we have a very good understanding of the space Xn in this particular case here. And by the way, the functions that we're looking at here are the functions that we call spline functions, or even more precisely first order spline functions or linear spline functions in example number 7 or 8. Yeah, I think it was example 8 in our long list of examples very recently. And that's why, because many people call these head functions here linear spline basis or linear spline basis functions. Okay, but I guess you can kind of see how by taking more and higher order head functions, or whatever you want to call them, if they are quadratic or cubic, you can somehow get higher order spline functions down here. Right, now back to the general method. What's the collocation method doing? It's trying to solve your equation ax equals b approximately as elements of your n-dimensional subspace Xn, which instead of the original equation solve the very same equation, but only on the grid points. Okay, so maybe it's time to zoom back in. While the original equation translates into the functions ax and the functions b have to be equal at every point t of the interval ab, your new equation only has to hold on the grid points. Okay, so needless to say, the setup was that A is an operator from our space X into our space Y. X is the space where we have introduced these funny basis functions up here, which give you, or which span this subspace Xn. And B here is an element of your function space Y, right? So of course you're not going to confuse the function b on the real axis with the point b on the real axis. You're grown up, right? So I hope it's fine with me giving the same notation to two completely different things. You're context sensitive. Okay, now this condition here means that your unknown function xn can be written as a linear combination like this of your basis functions. But of course you don't know the coefficients yet. These are now the unknowns, right? Well, originally x was the unknown. Now we replace that complicated problem by this simpler finite dimensional problem, where now this function xn in the finite dimensional space capital Xn is the unknown. And now we expand this unknown function xn in terms of our basis b1 to bn, and now the unknowns are just the coefficients. So now we're down to real numbers. Okay, so what you have to do now is, of course, you just take this expansion and plug it into that equation here, and by doing so you get the following equations. So the first equation is what you get when you put t equal to the first grid point. So you're expecting that equality to hold for t equals t1, which is why you see t1 here. Okay, and in place of xn, I've just squeezed in the expansion of xn in our bases with the unknowns alpha 1 to alpha n. Okay, and then you carry on and write down the same equation for the next grid point and the next, and so on until you arrive at the last grid point, tn. Okay, and that of course looks like a perfect match because we have n equations for n unknowns. And fortunately, A is a linear operator, so of course we can get all these summations out of A and all the little alphas out of A. And then our system of n equations looks a little bit different. So the operator A is simply applied to the basis functions, in our case the little hat functions, b1 up to bn, which gives you a new function. That new function is evaluated at the grid points t1 in the first equation, t2 in the second equation, and so on, tn in the last equation. Okay, and that's your system. Now it's obviously a linear equation in the unknowns alpha 1 up to alpha n, and that becomes even more visible when you rewrite it as matrix times vector equals vector. Okay, and now you finally arrive in your linear algebra course first year. So this is what you call an n by n collocation system. Okay, we're pretty much happy at this point. Well, maybe almost. In the headline of section 3.5, we announced examples of projection methods. And we know what projection methods look like. So the system that you get in the end, or maybe the system that you come up with here, should be written as A squeezed between two projections that both converge to the identity. Maybe it's not quite obvious how to choose the projections Pn and Pn hat to turn it into exactly this collocation method that we saw. But we give you a chance to do so in problem 15. Okay, and that was the collocation method.